Pre-training a foundation model takes months and massive compute, but teaching that model to process long documents, expanding its context window, happens entirely at the end of the pipeline, in a distinct phase called mid-training. This creates a severe logistical problem. Machine learning engineers must commit to their core architectural design long before they ever get to test how the model behaves over an extended context. During those initial months of pre-training, the standard dashboards offer a strong sense of security. The loss curve drops smoothly, perplexity stabilizes, and short context benchmarks glow green. This chart shows the performance of 26 models on the Helmet 32K benchmark. Despite having identical training data, the models exhibit a 26.5-point spread. In practical terms, the worst architectures lose 47% of their retrieval capability compared to the best. If you try to compare live production models like Llama 3, Olmo 3, and Qwen 3 to figure out why this gap exists, you hit a wall. Their training data, tokenizers, and optimizers are entirely different. You cannot isolate the architecture from the training pipeline. A 2026 paper titled Cracks in the Foundation isolates the architecture directly. The authors prove that when you hold the data constant, seemingly minor, highly defensible design choices combine to strictly cap the model's capacity for attention expressivity. The combination of micro-decisions made on day one dictates a model's long context ceiling. These architectural choices create a threshold that high-quality data cannot bypass. To run a valid architectural A/B test on a foundation model, you have to eliminate every variable that could influence the final score. The diagnostic pipeline OlmPool locks the exact pre-training data across 140 billion tokens. It locks optimizer variables, standardizing learning rate and batch size on Olmo 3. Finally, it locks the RoPE-theta adjustment and 10 billion token extension recipe. Generating this diagnostic pool requires immense compute. The researchers trained 26 discrete 7 billion parameter models, burning through roughly 170,000 H100 GPU hours. Because the control surface is entirely frozen, the only variable shifting across these 26 runs is the specific configuration of 4 architectural axes. Freezing these parameters is the only mathematically rigorous way to prove that a failure in long context retrieval is an architectural defect, rather than a side effect of a bad data mix. The first choice is applying QK norm to the query and key tensors. Engineers use this to tame logic variance, bounding numbers to ensure stable training. The second choice is grouped query attention, or GQA. GQA shares the same key and value matrices across multiple query heads, shrinking the KV cache and cutting memory requirements. The third choice is sliding window attention. Interspersing strictly local token windows among global layers further limits memory overhead for large prompts. The fourth choice restricts pre-training context length to 4,000 tokens. Shorter context pre-training maximizes tokens per second throughput. It keeps the activation memory small and reduces compute costs. In isolation, every one of these micro-optimizations is a highly defensible, rational choice for a machine learning team trying to ship an efficient model. These exact features are currently deployed across the ecosystem. Depending on which family you look at, Llama 3, Qwen 3, or Olmo 3, you will find variations of these specific switches flipped on. But because these decisions are made by different teams trying to solve specific, isolated problems, like stability here and inference efficiency there, the cost of their interaction remains untested. The standard engineering assumption is that architectural degradation would surface early in the pre-training phase through validation warnings. This chart illustrates the predictive failure of standard metrics. Pre-training loss correlates to long context performance with an R² of 0.29. In-loop benchmarks drop to 0.17. Pre-extension Helmet 8K reaches only 0.32. For an engineer monitoring a multi-million-dollar training run, the dashboard reads green the entire time. There is no drop in perplexity or spike in loss to indicate the foundation is compromised. The metrics designed to evaluate immediate token prediction are blind to the structural damage these features cause to long context expressivity. To accurately predict a model's downstream performance, we have to look past the individual performance metrics and simply count how many of these 4 expressivity-reducing features are present in the architecture. This basic integer count is the single most powerful predictor. Its in-sample R-squared correlation hit 0.67, outperforming any per-axis regression. A single feature alone causes minimal harm. Adding sliding window attention to a full attention configuration drops the model's benchmark score by a minor 1.1 points. But these penalties stack non-linearly. When you take that exact same sliding window attention mechanism and add it to an architecture that already uses grouped query attention, the result is a 9-point performance collapse. We can apply this heuristic to a hypothetical model configuration matching the structure of Llama 3. It utilizes headwise KK norm, sliding window attention, and grouped query attention. Based on the OlmPool data, possessing 3 of these 4 features places this architectural configuration mathematically into the lowest possible performance tier for long context retrieval. The damage to the model is not driven by any single design choice being inherently flawed. The failure is dictated exclusively by the compounding weight of multiple choices. This graph shows standard transformer attention distribution over a long document. We see a sharp, highly localized peak targeting the earliest tokens, but introducing QK norm to stabilize the model entirely flattens this distribution. It raises entropy, spreading the attention mass out evenly. Those early, highly focused token positions are known as attention sinks because they consistently absorb significant attention mass. Historically, these sinks were viewed as a pathology to be eliminated. But in a model without a dedicated focusing mechanism, these sinks actually operate as the default focusing structure necessary for precise long context retrieval. Flattening them removes the model's ability to focus. Because the short context dashboard cannot detect the loss of this internal focusing structure, engineering teams require a new workaround to validate their architecture before fully committing. The solution is to pause early in pre-training and launch a context extension probe at exactly the 70 billion token mark. This early test is reliable. Research confirms the architectural performance ranking established here remains flawlessly stable through a 2 trillion token pre-training run. Micro-optimizations silently compound to destroy a model's long context capability. To build capable foundation models, engineers must stop optimizing features in isolated silos and proactively count the architectural cracks early in the training lifecycle.